Welcome to The Explainer. Today, we're tackling one of C programming's absolutely most frustrating mysteries. If you've ever spent hours just staring at your screen, questioning your life choices because your seemingly perfect code suddenly crashed out of nowhere, well, you're in exactly the right place.
Right, let's just dive straight into it. Why is it that trying to change one single measly letter in your code can randomly trigger a fatal segmentation fault? We've all been there. It's basically a rite of passage for C programmers. So today, we're going to visually dissect exactly what happens under the hood to cause this, investigating the victim. To solve this whole thing, we kind of need to treat the crash like a crime scene. Our victim, the string literal. Simply put, it's just any text wrapped in double quotes. Whether it's the word university assigned to a pointer, or that classic hello world hanging out in a printf function, slapping those double quotes on it creates a string literal. Now follow this fascinating 5-step journey your code takes from your text editor all the way down to execution. When you type university, your compiler specifically packs it into this lockdown section called .rodata. That literally stands for read-only data. The linker grabs these sections, and then the operating system loader actually steps in and explicitly marks that chunk of memory as read-only. So by step 5, when your program is actually running and you try to write to it, the hardware itself shuts you down. And that perfectly explains exactly why the crash happens. Your computer's memory has permissions, kind of like files on your desktop. Your string gets read permission, so, you can look at it and you can print it out. But it gets absolutely zero write permission, and the hardware is actively enforcing this. Trying to bypass hardware-level security? Yeah, that's exactly what throws that fatal core dump. Time to look at some raw hex.
Okay, let's grab some forensic tools and actually look under the hood. To do this, we need to talk about hexadecimal dumps. Think of this as looking at the matrix code of your computer. It's just a way to translate and view the raw, base 16 data physically sitting in your memory. It looks totally intimidating, I know, but it's just the absolute, unvarnished truth of what your machine is holding.
For our first method, we're going to use the strings command right in our terminal. If we scan our compiled executable file, strings hunts for human-readable characters. And boom, there it is. Our exact string, university, is physically sitting right there, permanently baked into the compiled file. If we want to go even deeper, the objdump command lets us inspect the raw hex data of that exact .rodata section we were just talking about. Here, we can reveal, byte by byte, exactly how the text translates into raw memory. You can literally trace the hex value 48 to the capital letter H, 69 to the lowercase o, all the way down to the null terminator at the end. The evidence is literally right there in the binary. So, here is the million-dollar question. If the text is permanently locked in read-only memory, how on earth do we ever safely modify text in C without crashing? The absolute crucial point here is understanding the fundamental difference between how your computer handles a string declared with a pointer versus one declared with an array. They might look pretty much identical in your code, but mechanically, they are worlds apart. When we compare the two, you'll see the pointer is forever stuck aiming at that unchangeable locked down .rodata section. But the array? It does something incredibly helpful. It actually takes that original string and creates a fresh, brand new read and write copy directly on your stack memory. And when we execute both of these versions side by side, the difference is immediate. The pointer version tries to change the first letter to a lowercase s, and boom, it triggers a core dump instantly because that memory is locked. But the array version, it just modifies its own personal copy on the stack, printing out S University flawlessly. No crash, just perfectly executed code. Time to uncover some hidden optimizations. All right, just when you think you have C memory management totally figured out, we get a major plot twist. You really have to remember that your C compiler is an incredibly clever piece of software. It doesn't just blindly translate your code. Sometimes it actively optimizes it in ways that completely hide the evidence from you. Take a look at this scenario. We can write an array version that works perfectly, replacing U with S. But strangely enough, when we run our strings command and search for the word university in the compiled executable, our terminal outputs absolutely nothing. The string just isn't there. So how is the program printing a string that doesn't actually exist in the file? Well, the answer reveals itself when we look at the raw assembly code. Instead of storing a nice, continuous, readable string in .rodata, the compiler decided to be hyper-efficient. And honestly, we really have to appreciate how clever this is. It literally chopped the text up into numerical hex chunks and embedded those numbers directly into the CPU instructions. In the assembly, it stored the letters making up whole Bartow as one massive hex number. Let's actually see how this builds dynamically. Step by step, the compiler is loading these massive hex numbers into the RAX CPU register and then rapidly pushing them right onto the stack memory. It's literally reconstructing the string piece by piece at runtime. It just pulls it out of thin air exactly when it needs it, rather than saving the whole string in advance. And this sneaky compiler trick explains a really weird anomaly. If you run the strings command and happen to see it output universe2 with a capital U at the end, this is exactly why. The strings tool scans the raw bytes, finds the letters for Hilberto, and then accidentally grabs the very next raw hex byte in memory, which just happens to be 48. In hex, 48 translates to a capital U. So the compiler's optimization creates this bizarre ghost string. It is literally the perfect recipe for a maddening invisible bug. Let's lock in some concrete rules for your C code. Now that we've fully investigated the memory layout and the compiler's sneaky tricks, let's establish some ground rules. These 4 takeaways are basically your survival guide. Number 1, always use arrays if you plan on modifying the text. 2, expect string literals pointed to by a pointer to be strictly read-only. 3, know that arrays are safe specifically because they make stack copies. And 4, always beware of sneaky compiler optimizations if you're hunting for strings in your binary. I highly recommend keeping this master reference sheet handy. It perfectly summarizes what you write, where it physically goes in memory, and whether or not you actually have permission to change it. Plus, it gives you those strings and objdump commands so I can quickly recall exactly where your text is stored when you're deep in debugging mode. Finally, if you absolutely must use a pointer and you need to change the text, the professional way to handle this is to allocate dynamic memory with malloc and copy the text over. So, I'll leave you with this absolute final rule. If you see a string literal in double quotes, automatically think read-only unless you've explicitly allocated memory. Now that you've mastered the illusion of string mechanics, what other under-the-hood C memory mysteries are you going to investigate next? Maybe conquering the dreaded double free?